All right. Hello, everybody. Welcome back to Anti-Algorithm Math. We're here to continue the proof of the Riesz Representation Theorem. Uh, if it goes well, I'm going to finish. And if it doesn't go so well, there will be another one. The last step is actually the hardest. And so I think if I leave anything out of this video, it'll probably be the last step. So just to remind you, I've put the statement of the theorem here that we did before. Here's the construction of mu and m, as well as this auxiliary um, collection mf that we're using as a tool. Um, and then we have started to prove the theorem step by step. And last time we got to step 5, which means we can do nothing else but go on to step 6. All right, so step 6 says um, if A is in MF and B is in MF, then uh, A minus B, A union B, and A intersect B are in MF as well. Okay, so I I looked this up because I thought this sounded like some kind of um, known thing. So when we have this basically means that MF is a sigma ring. Okay, so sigma ring is a known thing. Um, And that's what these conditions say. So, you can compare them to the conditions for a sigma algebra that allow countable unions and complements, which allows also, countable intersections. Um, Obviously, we can do, relative complement or subtraction like this, right? So sigma algebra is stronger than this because we have all three of these, but a lot more, right? But you'll see as we go through the steps that MF is really the sets of finite measure. So this is the video where I learn why it's called MF. It's called MF because it's the collection of sets of finite measure. Okay. So, uh, yeah, I think I had a comment in the last video about that, and now I know the answer. Okay. So, if or yeah, so let's let epsilon be greater than 0. Then by step 5, um, there exists k um, k a uh, k b v a and v b um, such that KA is contained in A, which is contained in VA. Um, Supposed to be uppercase A. Uh, KB is contained in B is contained in VB. And the measure of the difference is less than epsilon, right? For both. All right. So, just so you remember, this is step 5. So K is compact and V is open. The notation already implies that, but just so you know, that's the case. Okay. So, since A minus B is contained in V1 minus K2, okay. Uh, So you might have to think about that for a second. Okay. So if you have an element of A that is not in B, then oh, sorry, I switched to Rudin's notation here. Sorry about that. I'm trying to use my own. So let's get that right. That's VA minus KB. There we go. Okay, so if an element is in A but not in B, then it's necessarily in VA and it's necessarily not in KB. Okay, that's straightforward. And then this is contained in VA minus KA union KA minus VB union VB minus KB. Okay. So if you have something that's in VA and not in KB, um uh then it's either here, okay? So it's either in VA but not in KA. But if it is in KA, then for sure it's not in VB, right? Um, uh, oh, that's not necessarily true. If it is in KA, maybe it's not in VB. But if it is in VB, then necessarily it's not in KB. Okay? Um, I kind of hate the way I wrote this KB, so let me write that one more time for you. There we go. Okay. Right? So it's kind of just a chain of subtractions here, right? This KA cancels that, this VB cancels that. That's sort of the idea. But if you think through what's in here, you should see that any element of this has to be in one of these three sets. It's fairly straightforward. Um, okay. So so now um so now by step one, okay? So remember, step one is countable subadditivity. Okay, so by step one, the measure of A minus B is less than or equal to the measures of these three, the sum of the measures of these three. So uh, the first two have or the first and the last have measure epsilon. So we get epsilon plus the measure of Ka minus Vb plus epsilon. Now Ka minus Vb is compact. Um, so this shows that A minus B is in MF. Okay, so remember what that means, everybody. So it means that, first of all, it means that it has finite measure. Finite measure is not hard to check because um, if A and B have finite measure, then clearly A minus B has finite measure. That's straightforward. Actually, only A is required to have finite measure there. Um, and then we have this condition which says that we can approximate we can approximate from below by a compact set. So, what we just proved here is that we could approximate from below. So you could subtract 2 epsilon from both sides here, and you'd get that the measure of this is greater than or equal to this minus 2 epsilon. So we can approximate this from below by that, right? And Ka is a subset of Ka minus Vb is a subset of A minus B. Okay, so and so let me just Let me just comment that. It's fairly easy to see. Okay, so we get that, and now we're just gonna leverage. Now we're just gonna leverage other stuff. So A union B is equal to A minus B union B. Okay, that's just kind of a silly way to rewrite the union, but so by step 4, A union B is in MF. So let me just remind you what we proved in step 4. So we'll go back to that. Here it is. So it says that for countable unions, if the countable union has finite measure, then the countable union is in MF if each of the individual sets have finite measure. Of course, we only have 2 sets here, so the rest of them are going to be the empty set. That's fairly straightforward. We're assuming they have finite measure, right? So there's no problem with that. And so this is in MF, this is in MF. So the union is in MF because we know it has finite measure. Okay? The union has to have finite measure by the countable subadditivity, right? So Rudin doesn't actually say that, but it's true. Okay. And then similarly, we can get the intersection as A minus B. All right, that's just a funny way to write the intersection. So this is an MF by above, right? Because we can subtract any 2 sets and stay in MF. Um, so we can subtract these two. Okay, so that proves that MF is a sigma ring. Let's go on. So next up, what we have is, oh, this is a big one. Step 7, which says that M is a sigma algebra, which contains all Borel sets. Okay, proof. So uh, so what do we need to prove that that it's a sigma algebra? We need to prove that um, that X is in there. That's non-trivial, but we do need to prove it. Or it's fairly trivial, but we do need to prove it. Um, actually, uh, we could do that right away, but Rudin does this slick thing where he buries it in uh, the first part of the proof that it contains all Borel sets. Okay, so uh, uh, so yeah, let me actually mention that right away. So if C is closed, then C intersect K is compact, where K is compact. That's a standing assumption here. Um, maybe it's worth reminding you what M is because we haven't talked about M as much as we have MF. So M is the set of all subsets that if you intersect them with a compact set, then you land in MF. Okay, so that's basically what that's the condition we're going back to here. Okay, so if I have a closed set and I intersect it with a compact set, right? I want to know that that's in MF, which means it has, well, it means all this stuff. But let's just now remember step 2. So um, step two says that if K is compact, then K is in MF. So, so now that tells us that um, C intersect K is in MF by step 2, and therefore C is in M by definition. Okay, so this proves that X is in M, for example. All right. It also proves that all the closed sets are in the sigma algebra. So if I now prove that the collection M satisfies is closed under countable unions and complements, then I will know that it also contains all Borel sets because it contains all closed sets. So if it's closed under complements, then it contains all open sets, and therefore it contains all Borel sets by definition. Okay, so so let's now say uh, that we have an A that's in M. Okay, then a complement intersect K, where K is compact, right? That's the compact set I'm carrying around. Okay, is equal to K minus um, A intersect K. Okay, and this is in MF. This is in MF by assumption, right? Because A is in M. So if I intersect it with a compact set, it's got to be in MF as well. So therefore, this whole thing is in MF by by the last step. What was it? 6? By step 6. Okay. So therefore A complement is in M as well. Okay. Cool. So, um, we're well on our way. We now know that the sigma algebra contains all open sets as well. Or, well, we don't know it's a sigma algebra yet. Now we have to show the countable union. Okay. So now if a bunch of AIs are in M, I love how like algorithms and AI and all that. Like if I say AI, they think I mean artificial intelligence. I don't mean that. I'm not talking about artificial intelligence here. I'm talking about a set that's labeled A sub I. Okay. So just a warning to all algorithm large language model stuff out there. Okay. Anyway, so we have these AIs, and we let A equal the union, just to have a shorthand for it. So I want to show that this is an M. That's my goal. Okay. Um, so now define recursively. So we'll start with B1 equal to A1 intersect K, and B n plus 1 equal to A n plus 1 intersect K minus the union of the previous B's. Okay, so then by assumption, we can see that the BIs are all in MF. Okay. Similar reasoning, right? We're using step 6 there, among other things, like the assumption that the AIs are in there. Um, so furthermore, and this is where things get a little more exciting. A intersect K is equal to um, the union of the BIs. Okay. Um, the BIs are in MF and disjoint. Okay. So notice that I subtract off the previous B's. So this is disjoint from the previous B's, right? And it's the previous B's are disjoint from it, right? That okay. If we subtract them, they have to be disjoint. Okay, so that means that the BIs are disjoint as well. Okay. Now, how do I know that this is true? So if I have something in A intersect K, then that means it's in some A sub whatever, right? A sub M, right? Intersect K, okay? Um, and if it's in um, if it's in one of the previous like B1 through BM minus 1, then all the better. Then it's there, right? If it's not in any of these, then it's automatically in BM, right? Which will be equal to BM intersect K minus the previous B's, right? Um, sorry, AM intersect K minus the previous B's. Because we already know it's in there, right? But it might be in one of the previous B's. But if it is, that's okay. It's still in the union. Okay? So there's no problem with this. Um, so so now that is in MF by step 4. All right. So remember that's what we proved back in step 4, right? We proved that if the union has a finite measure, then we have this. Okay. Uh, so if they're pairwise disjoint, right? So yeah. So um I think the only thing that I want to say here is that the union here has finite measure because it's equal to A intersect K, right? And uh, A intersect K is, among other things, a subset of K, right? Which has finite measure because it's in MF, right? So if it's a subset of that, then it's gotta have finite measure. So that's the only lingering issue here. Okay, so that now proves that this is a sigma algebra and it contains all closed sets, which means it also contains all open sets, which means it also contains all Borel sets. Victory. Okay. So let's continue. Step 8. Okay. So here is step 8. MF is equal to precisely the sets that are in M um, whose measure is finite. Okay, so this now will prove that every set in MF is in M also, and it specifically characterizes these as the sets of finite measure, the measurable sets of finite measure. Okay, so let's go ahead and prove this. Okay, so if E is in MF, uh, then by steps 2 and 4, or sorry, not 4, 6, VI, not IV. steps 2 and 6 imply that E intersect K is in MF for K compact as usual. So therefore E is in M. Um, yeah. So this is basically proving that MF is a subset, right? So let's talk through steps 2 and 6. So step 6 was this stuff, okay? In particular, the intersection, okay? And then step 2 is what tells us that compact sets are in MF. So basically, if we know that E is in MF, K is in MF, then the intersection's in MF. So it's a subset. Okay, we're done. All right, so now we know that MF is a subset of the sets of finite measure. Okay, so now we'll go the other way and let E be in M such that the measure of E is finite. Okay, so what do we need to show now? Um, we basically need to show that it can be approximated from below by a compact set. Okay, right? Because that's the real extra condition, right? That we need to be an MF, right? It's got this other condition here. That's the one we're missing. Okay, and that's approximation by compact sets. All right, let epsilon be greater than 0, as we always do. Okay. Um, there is an open V containing E such that the measure of V is finite. Um, that just comes from the definition of the measure. Okay. Um, by steps 3 and 5, um, there is a compact K uh, contained in V with the measure of V minus K less than epsilon. Okay, so let's go back to 3 and 5 so we understand why we're talking about 3 and 5. Okay, so this is step 3, okay, which says that the measure of an open set, can be uh, approximated from below by compact sets. Okay, so that's worth knowing for sure. Um, okay, and uh, and now uh, yeah, so that's step 3, and then step 5 is this. Okay. So um, okay, so basically what we're doing here um is step I already forgot what I'm on here. Right. Step 2. Okay. Uh no, step 2 is not what I'm talking about here. Step 3. Here we go. So step 3 says that V is in MF if the measure is finite. Now remember, we assumed that. We didn't assume that. We built V to have finite measure. So our set V now um, is actually a valid choice for E here, right? Because V is in MF. So that means there exists a compact K and an open W, say, with this property. Okay. So I guess W is kind of extraneous here, but basically we're taking K contained in V contained in W with um, the measure of W minus K less than epsilon, and therefore we get this, right? So that's basically what steps 2 and 5 produce, and clearly it's good enough to get the thing that we want here, which is this compact set um, uh, contained in V. Okay, so since E intersect K is in MF, I want to make sure yeah. I'm always paranoid that I'm not recording. Okay, since E intersect K is in MF, there is a compact um, H contained in E intersect K with the measure of E intersect K less than the measure of H plus epsilon. Okay, this is the way Rudin writes it. I don't know. I would put the minus epsilon on the left-hand side, but anyway, just to be a little more obvious about it. But remember that's the defining condition of being an MF is that you can approximate it by compact sets that are contained in it. You can approximate it like its measure. Um, okay, uh, since E is a subset of E intersect K um, union V minus K. Okay, so just to put all that together, V contains E, right? So this is even larger than E. Okay. So if I had E minus K here, this would be equality, but because I put V there, it's actually a larger set. Okay. It follows that the measure of E is less than or equal to the measure of E intersect K plus the measure of V minus K, um, which is in turn less than measure of H plus 2 epsilon. And that shows that, again, we can approximate the measure of E from below by a compact set. So that all together means that E is in MF, and that's what we wanted to prove. Uh, yeah, right? Yeah. All right. I got confused for a second what we were actually trying to do. Yeah. So we were starting with this with a set of finite measure, okay? And we squeeze that set of finite measure. Um, we sort of split up that set of finite measure into this V minus K, right? So we get rid of basically a big chunk of this. I shouldn't say a big chunk because the measure is actually small, but we sort of break off this V minus K so that we can then focus on E intersect K. The idea is, again, we're trying to approximate E by a compact set. Um, uh, so, um, so we want to focus on E intersect K, but we need to deal with the part that doesn't intersect K. And that's exactly what this does, right? It gives us a small chunk that contains all of the stuff in E that doesn't contain intersect K, right? And that tells us that we're pretty close if we can approximate E intersect K. So E intersect K is close enough, right? Within epsilon. So that means the whole thing is within 2 epsilon of the compact set I want. And I'm done. Okay. All right. So we're on to step 9. Oh, you know what? I forgot to declare victory. I have 2 victories to declare. So here we proved that M is a sigma algebra. Okay, so let's go back because I wanted to like check off things. It's been a while since I actually proved anything, but M is a sigma algebra. I have now proven, and further, uh, let's see, where was that? I guess that was here. Okay, if you look at this, the consequence of this um, is uh, is part D. Okay, so this is part D. If E is open or E is in M and has finite measure, so that means E is in MF by that step, then it satisfies this condition to be an MF. We already know that open sets are in MF, so we're finished with part D. Um, okay, so I mean that I just it's worth like keeping track of where you are, especially in a very long proof like this one. Okay, so now let's go on to step 9. You're gonna like this one a lot. So step 9 is mu is a measure on M. Proof. Okay, so obviously we need to prove this. Okay. Um, so basically we need to prove countable additivity. Okay. So we want one to show that um, the measure of a union I equals 1 to infinity of EIs is equal to the infinite sum for EI in M. Now, if the measure of EI is equal to infinity for any I, then done, because they're both infinity. Okay, so that's pretty straightforward, right? So basically, I just need to prove this when all the EIs have finite measure. If the measure of EI is finite for all I, then EI is in MF. So done by what was it? Step 4? I always forget what anything's called. Yeah, by step 4. Step 4. Okay. Yeah, cool. Yep. So that's it. All right. Um, so that's another one, right? That's another big victory to appreciate. Okay, so now we have shown, in addition, that mu is a positive measure. We've shown that it's unique, right? We did that at the beginning. Okay, so there's only one thing left to prove at this point. And the thing left to prove is this, that that it represents lambda. Okay. Now this is the hardest proof. Okay, this is the hardest step of them all. It's also the most powerful, right? I mean, this is like the main thing we want here. Okay. So let's try to do step 10. Can I do it? We're gonna find out. So step 10, buckle up. This is gonna be a multi-page step, I'm sure of it. So step 10 says for f in the continuous functions with compact support on x, we have that lambda of f is equal to the integral over x of f d mu. Okay. And that's part A, right? That's all that's left. Okay. So clearly it is enough to prove this for real f. And in fact, if all you care about is real functions, then we don't even need to worry about the complex case. But basically, the complex case is taken care of by the linearity once you have it for real functions. Okay? Because you can split a continuous function compact support into like real and imaginary parts, and then apply the linearity, and you'll get the result for complex f. So it's a trivial extension, but we're just going to prove it for real f. Okay. Also, we can prove without loss of generality that lambda f is less than or equal to the integral. Okay. Um, since uh, negative lambda f is equal to lambda of negative f, it would be then less than or equal to x, the integral of negative f d mu. I mean, these are both linear, right? Okay. So, uh, uh, yeah. So if we have the inequality going one direction for all real f, okay, so we have this inequality for all real f, then we automatically get the other inequality just by linearity. Okay, so basically we're just gonna prove this inequality here. All right. Okay. So that's my plan now. Okay. So now we assume that f of x is subset of R, real numbers, okay, where f is continuous function with compact support, okay. Let k equal the support of f, so it's compact by assumption, okay. And then since we have a compact subset, um, uh, since we have a compact subset, sorry, there's a weird note that's being made here, so I just want to remember what that's about. Oh yeah. Um, um, so choose A and B so that f of x is contained in the interval from A to B. Okay. So the range of f has to be compact because the image of a compact set is compact. And remember, the support has all the points where f is not equal to 0. So basically, the range of f is the range restricted to the compact set K and 0, right? Possibly 0. I mean, I don't know for sure that 0 is in the range, but it might be. But that's okay because the single element set 0 is compact. So that means the range is compact. So that means it's contained in some finite interval, finite closed interval in this case. Okay, so I'm allowed to do that. So now let epsilon be greater than 0. Okay, and choose. So now we're going to sort of partition yi's so that yi minus yi minus 1 is less than epsilon, and y0 is less than a is less than y1 is less than y2 all the way up to yn, which will be actually equal to b. Okay, so the interval from a to b is a finite interval, right? So if you give me an epsilon, I can split that interval into finitely many pieces that are smaller than that epsilon. So this n might be like 80 billion, but it's still finite. Okay. And for technical reasons, I'm letting y0 be less than a. Okay. I'm definitely allowed to do this. Okay. If we just make this distance smaller than epsilon, then I can just choose y0 like close enough to a to squeeze it in there, right? Because there's still some distance to maneuver in when you have a strict inequality. Okay. I mean, this is very, very elementary stuff. Again, I don't say that to scare you. I say that just to emphasize that um, this isn't like some kind of some kind of fancy advanced math thing. Okay. So all right. Let's let me do it on the next page actually. Now we have this little partition. On the new page, we'll let EI be defined to be the set of X in X, of course, such that yi minus 1 is less than f of X is less than or equal to yi intersect K. Okay, which is the support of F, just so you remember what K is. It's the support of F. Okay, all right. So since F is continuous, it is Borel measurable, right? The inverse image of an open set is an open set. We know that the open sets are all in the sigma algebra, right? M, it contains all Borel sets. We just said that. So therefore it's measurable. Like M measurable. Okay. Um, and because this is an inverse image of a half open interval, right? Which a half open interval is definitely a Borel set, right? Um, right? I guess, yeah, maybe I should clarify there. Yeah, well, whatever. Um, half open intervals can be realized as like uh, the uh, like an open set minus another open set, for example. And so, by the sigma algebra properties, I know that the EIs are all going to be um, uh, uh, Borel sets, um, right? So, um, and the EIs are Borel sets. All right. So they're not necessarily open or closed, but you could obtain them from that sigma algebra very easily, right? So they're all Borel sets, um, and are disjoint. All right. It's fairly easy to see that they're disjoint because I have a strict inequality here and I have less than or equal to there. So these are disjoint with um, the union from I equals, did we start from 0? Uh, no, no, no. We're starting from one. Right, right, right. Because this is I minus one. So I equals one to n of the EIs. Um, the union here will be K. Okay. So we know that this collection here, like taking out the intersect K, we know that encompasses the whole space X, right? Because the range of F will always land in one of those. Okay, one of those little half open intervals, right? So every X then has to be in one of these sets. So if I then intersect that union with K, then I get everything in K. Okay? All right. So that's fairly straightforward. Um, Now there are open sets VI containing EI, um, such that, I think you know where I'm going with this one, right? This actually goes back to the definition of the measure. So the measure of VI is less than the measure of EI plus. So I could put epsilon here, but I'm going to put epsilon over n. I think epsilon over other stuff would work too, right? I'm gonna add these up, and I don't want the fact that I have like n of these points to cause me a problem later, right? So I can divide epsilon by like 40 billion if I need to. It's still gonna serve, right? So this is totally fine. Okay, so now we have this, and such that f of x is less than yi plus epsilon for all x in vi. Okay, so I know that there are open sets like that. How do I know um, how do I know that I can also insist on that connection, right? Well, I simply need to take the VI that I get from the definition, okay, and then intersect it with the inverse image um, of this infinite like open interval here, right? Everything below this, right? If I take the inverse image via f of that set, you know, that's going to be like for sure measurable, for sure, open actually, for sure. And then I can intersect that with the open set that I get from the definition of the measure mu. And that set will only have smaller measure. It'll still be contained in EI, right? Because remember, this is EI. So if I take the inverse image of this half open interval, it's going to contain EI for sure. Okay. Uh, I mean, it's going to contain this, and therefore it's going to contain EI, right? So then that gives me an open set with the properties that I need. Okay. Okay. Now, by partition of unity, you had to know this was coming. By partition of unity, there are functions hi less than the vi's, such that, um, so remember, the vi's, the union of the vi's contains k because, the union of the ei's is equal to k, okay? So such that the sum of the HIs is equal to 1 on K. Okay, going back to the partition of unity result from part whatever that was. I'm sorry, I don't remember where I said anything. Um, But I covered it in a previous video. It's also in the book, right? So it's theorem 2.13 if you want to consult the book for that. Okay, hence F is equal to the sum of the HIs times F. Okay, so we went through this before, right? I know this is true on K. But remember, K is the support of F. So if I'm not in the support of F, then F is equal to zero and it's also true. Okay? That is the beauty of a partition of unity sort of argument. And that's why we're so interested in the support, right? The support is really a thing that does a lot of work in these arguments. Okay. So now since we have this, um, step two shows um, step two. So, okay, hold on. What's step two again? It's been so long. Oh, right. So, step two shows that for compact sets, it's the infimum of functions that are above k, right? Functions that are above k. Well, um, you know, we just showed, or we just stated, that the sum of these HIs is um, one on K, right? So since the HIs there's finitely many of them. I'm not writing it as a finite sum because Rudin doesn't, and because it's just unnecessary notation. But it is a finite sum of continuous functions with compact supports. So it's a continuous function with compact support. Okay, and it's equal to one on K. Okay. So far, so good. Oh, actually, let me review one thing here. Um, yeah, yeah, yeah. So, like I could technically divide by its max if its maximum value is greater than one, I could do something here. But I'm not going to bother with that. Basically, by step two. All right, you can think through this if you want, right? There's technically like something to think about in terms of that sum being greater than one sometimes, right? Um, just to apply this, but actually that's not a problem at all if you think about it. Um, right? It's a continuous function with compact support. All these functions are positive, right? So it's a positive function for sure. And so it has some maximum value. We can just divide by that maximum value and preserve the properties that we need. I mean, we can do that like off of K. Anyway, whatever. No, no, no. Hold on. This is now disturbing me. Let me think for a second. Okay, actually, this is a subtle point that I didn't pick up on, but by construction, if you go back to the proof of partition of unity, which is what I just reviewed here, if you go back to the proof of partition of unity, you'll see that uh, the way we prove that the HIs add up to one, um, actually shows that the sum of the HIs is less than or equal to one everywhere. Okay. So, um, so like that isn't stated in the result, but it is true. Right. So, it's just worth noting here because of what I want to say next. Okay. Sorry, I needed to get that detail I needed to get that detail right before we move forward. Okay. So now I know that uh since K is less than the sum of the HIs, we have that the measure of K is less than or equal to lambda of the sum of the HIs, which is in turn equal to the sum of the lambda HIs, just by linearity. Okay, simple linearity. Okay, uh, so we have this. And now, since HI times F is less than or equal to um, yi plus epsilon times HI. Okay, so you might want to uh, think about that for a second. Okay, um, so if you're in VI, so just remember um, that this holds for X in VI. Okay, so this is less than this if we're in VI. Check. What if we're not in VI? Okay. So remember then that um, oh, I didn't say this actually. Oh, yes, I did. We have this. And what does this mean? It means the support of H is contained in VI. So if we're not in VI, then HI is equal to 0, and we have equality. Okay. So that's fairly easy, but it's worth saying. And yi minus epsilon is less than f of x on ei. Okay, uh, yeah, hold on. Oh man, it's so easy to get confused. All right, so this is true by just by this definition, right? And by the fact that the distance between two consecutive yi's is less than epsilon. Okay. So if we subtract epsilon from yi, then we have to end up over here, which would be less than f of x. Okay. So that's why that's true. Okay, and now we're ready for the big punchline. So here it comes. Lambda f is equal to the sum of the um oh, now we're naming it. Oh, right, I see. Oh, right. There's the same number. Okay. All right, hold on. Hold on. So remember, the HIs come from this partition of unity, right? But we know how many VIs there are. They're the same as the number of EIs, and the number of EIs is the same as one less than the number of Ys, which is to say there are n of them. Okay, so that's why we're summing to n here. So we're just using linearity. So just remember this, okay? So so that means by linearity, we get a sum from I equals 1 to n of lambda of hi times f. Partition of unity is basically designed for this to move the problem to a local place, okay? And then lambda of hi times f because of the inequality above, right, and the monotonicity, this is less than or equal to the sum I equals 1 to n. And I'm going to use linearity here of yi plus epsilon times lambda hi. Okay. Okay. And now there's some algebra here. Okay. This is equal to the sum from I equals 1 to n of the absolute value of a plus yi plus epsilon times lambda hi minus the absolute value of a times the sum from I equals 1 to n of lambda hi. Okay, and there's a times there. All right, so I mean, one thing that's pretty easy to see right away is that this and this will cancel each other out. Okay. And what we're left with is yi plus e times that, which is what that is. Okay, so actually that was pretty easy algebra there. Cool. Now, this is less than or equal to the sum from I equals 1 to n of the absolute value of a plus yi plus epsilon times the measure of ei plus epsilon over n minus the absolute value of a times the measure of k. Okay, so where does this all come from? This all comes from the fact that let's see. The k part, right? The fact that k is less than this sum, right? That's what we talked about at the bottom, right? At the bottom on this page. Okay. Now, why is lambda hi less than or equal to this? Okay. Um, uh, that would be the next question. Okay. And just going to take a moment to think about that. All right, so it's not too bad. So putting it all together, um, remember that um, hi is less than vi. Okay, so if you go back to like the original definition of the measure, this first step is we define the measure of an open set as the supremum of the functions that are less than that open set. So that means lambda hi is less than the measure of vi. Okay, but in turn, we know that, stopping too soon here. In turn, we know that the measure of vi is less than this. So that means this is less than that, and that explains this inequality. Okay. Now you can do some more algebra because this is an equality here. Sum I equals 1 to n of yi minus epsilon times the measure of ei uh, plus, yeah, and this is outside of the sum here, just to clarify, 2 epsilon times the measure of k plus e over n of the sum from I equals 1 to n of the absolute value of a plus yi plus epsilon. Okay. So I had a real blast in my notes like justifying this equality. Um, it took me like a page of calculation Okay. Um, so you should keep in mind what we're trying to achieve here. Um, and what we're trying to achieve is what we're trying to achieve is what am I trying to say? What we're trying to achieve is an inequality that has the integral of f um, over on one side, right? So uh, the reason why we're writing this is because this here is the integral of a simple function, okay? And we observed that of the values of that simple function are less than the values of f on EI. So basically, uh, uh, this is an approximation to the integral of f by the definition of the Lebesgue integral, which I talked about maybe in the first video. I think it was the first video. Um, okay, so like the whole point of this is we're trying to find a simple function that's close enough to the integral of f that we can then relate our linear functional to that to the integral of that simple function. And the nice thing is, the integral of that simple function can sort of be realized by not exactly by, because we're approximating here, but we have a good idea of how the connection between values of the linear functional and measures, right? So we're just leveraging that to give us a simple function, okay, that will approximate the measure of f. So now we can see that uh we have like all this stuff, okay, um all this stuff that we're going to add up, like n times, but we've divided by n here. So that's the other part of the story. We have an epsilon factor here and we have an epsilon factor here, okay? And all of this is totally controlled and fixed, right? It's not the value of n is arbitrary here, right? So it could be a problem except that um, we divided by n there. So um, I was really hoping it wouldn't do that, but it did do that. So I guess as soon as I lift the highlighter, okay, there we go. So the point is that this whole thing here is going to be tiny, and this thing here is like a simple function. So let me write that out explicitly. So this is equal to the Lebesgue integral of the sum from I equals 1 to n of yi minus epsilon. So, we're creating a simple function that will do the job that we want it to do, right? And so that's why we're splitting up the range, right? To give us a simple function um, that works. Okay, d mu. Okay, so that's what that is. Okay, and this comment up here shows that our simple function of the sum I equals 1 to n of yi minus epsilon times the characteristic function of ei is less than or equal to f, right? And that's simple, okay? It's a little bit of messiness in here that I'm not totally happy with. So let me try to fix that. Okay. So that gives us a simple function that we can then use um, to approximate, right? And that's basically the idea here. Okay? So so now so plus epsilon times a bunch of stuff. I'll write down officially what it is 2 times the measure of k. That's fixed and determined by f. Plus the absolute value of a, which is fixed, determined by f, plus b, which is fixed, determined by f, plus another factor of epsilon. Okay, so I mean, epsilon's arbitrarily small here. So, if we let epsilon go to zero, this whole thing's going to go to zero, right? And this up here is less than or equal to the integral over x of f d mu, right? Because we have a simple function that's less than or equal to f. To be clear, this doesn't have to be positive, right? We're not actually dealing with a positive function necessarily here. Okay, but we still have monotonicity in the integral. So we know that this will be less than or equal to that, right? So that's the good news, okay? So plus epsilon times some constant. And so that now means that lambda f is less than or equal to the integral of f d mu. And guess what? That's what we wanted to prove. Oops. So with that, oh my. With that, we now have achieved part A. Boom. And that means we have achieved the entire theorem. All right. So that last step, uh, I invite you, okay? It's an exercise for you because I did it, but I don't know how instructive it is to sit here and do intricate algebra in front of you. But I certainly invite you if you want to show why this is equal to that, right? It's not that hard. Like for example, you can see that if we oh, I did not mean to do that. I always mean to pick a highlighter and then I don't. If we take this times this, it's going to give us that. All right, so that's where that comes from. Okay, and then you can think about putting some other stuff together, um, and see what happens. Uh, this. Um, well, anyway, I leave it to you to do that. It's a fun exercise if you're into that sort of thing. Um, so yeah, I'm done actually. All right, so that was the whole point of this series. So, oh, you know what? There's one more thing I want to say. There's one more thing I want to say, and I feel like this series wouldn't be complete without this. Now, proof. Oops. Let's uh let's go back. Undo, undo, undo. Okay. That color back. Okay. Now we will show that the measure of the interval from 0 to 1 is equal to 1, right? The length of the interval. Okay, so I'm going to apply monotone convergence. Okay, to the sequence f, oops, fn. And I'm just going to show you what fn is by a graph. So here's 0, here's 1, here's 1 up here. So I'm going to put 1 over n here, and I'm going to put 1 minus 1 over n, or n minus 1 over n over here. I'm going to put a point there. I'm going to put a point here. It's going to be straight line here. And then we're going to drop down to here and drop down to here at the end. Okay? So, and you can let it be 0 outside of this, right? So equal to 0 everywhere else. Okay, so Fn is a continuous function with complex support on R, right? You can clearly see that the support is contained in the interval from 0 to 1. So if we take the closure, I mean, you know, it's going to be the interval from 0 to 1. Okay, we also have that it's a monotone sequence. Okay, and it converges to the characteristic function of 0, 1 pointwise. Okay, so um, uh, if we look at the Riemann integral of Fn dx, what is that equal to? So now this is something that you can feel free to do formulaically if you want. I invite you to do it, okay? But, if you just think about the areas here, like triangles and squares, right? It's not deep, and there's even symmetry here, right? You could like move this over and you could clearly see that the area of this is going to be um n minus 1 over n, right? Like that's pretty clear, I think. Um so so uh I invite you to calculate that at your leisure. Okay. Like you can write a formula for this function if you want, and you can actually use like the fundamental theorem of calculus and you can figure out the area from that, right? But it's pretty easy to see that this is equal to this, okay? But by the Riesz representation theorem, this is equal to the integral over R of Fn d mu. Okay. Um, right? Because we just so if you remember what the point is that if we start with the Riemann integral, that gives us a positive linear functional on the continuous functions with compact support, and the measure that we get out of that is the Lebesgue measure. Okay, and I don't just mean a Lebesgue type measure. I mean like the Lebesgue measure on real numbers, for example. Okay, so that transitions over to Lebesgue integral, which then converges to the integral over R of the characteristic function of 0, 1, okay, by monotone convergence. Okay, so that is then equal to the measure of the interval from 0 to 1. But on the other hand, this sequence converges to 1, so these two are equal. Okay. All right. So that's the thing I really wanted to end on. Um, I wanted you to understand as well as you could um, that the measure that we get if we use the Riemann integral in the Riesz representation theorem is the Lebesgue measure. And obviously this doesn't prove that it's a Lebesgue measure, but you could sort of extend this proof to show that for any open interval, the measure of that interval is the length. And once you have that, it doesn't take too long to see that it's the right thing. That's not necessarily how you would prove that it is Lebesgue measure. I mean, you could prove that, it contains, it agrees with Lebesgue measure on Borel sets and so on, right? But I think it's a hop, skip, and a jump from there once you know some properties of Lebesgue measure that you've constructed some other way. Okay, but I mean this is just too cool, so I had to throw this in and extend the video just a little bit. But hopefully that was a fun series for you. I will be back eventually with some other advanced math thing. I will just have to think about it. Um, so give me a little time, throw in some requests, rate, review, and subscribe. Thank you for watching, and I will see you next time. All right, bye everybody.